Imagine a world where sunlight collected during the day could be stored directly inside a liquid and then released hours, days, or even years later as usable heat without relying on traditional batteries or the electrical grid. Scientists at the University of California, Santa Barbara have now taken a major step toward making that vision possible. In a remarkable new breakthrough, researchers developed what they describe as a rechargeable solar battery, a molecular system capable of capturing solar energy, locking it inside chemical bonds, and later releasing that energy on demand as heat powerful enough to boil water. The achievement represents a fundamentally different approach to renewable energy storage and could open the door to entirely new ways of using solar power long after the sun goes down. One of the greatest limitations of solar energy has always been storage. Conventional solar panels work well while sunlight is available, but once night arrives or clouds block the sky, electricity generation rapidly declines. Current solutions typically rely on large lithium-ion battery systems to store excess power for later use. Although effective, these batteries are expensive, resource-intensive, and limited by degradation over time. The new research explores a radically different strategy. Instead of converting sunlight into electricity first and storing that electricity in batteries, the system stores solar energy directly inside specially designed molecules. In essence, the molecule itself becomes the energy storage device. The technology belongs to a growing field known as molecular solar, thermal energy storage, often abbreviated as MOST. The central idea is surprisingly elegant. Certain molecules can absorb sunlight and rearrange their atomic structure into a higher energy configuration. This new form remains stable, effectively trapping solar energy inside the molecule like a compressed spring. Later, when triggered by heat, a catalyst or another stimulus, the molecule snaps back into its original structure and releases the stored energy as heat. Unlike conventional batteries, which store electrical charge, these systems store sunlight directly as chemical strain energy. To create this new material, the researchers focused on a modified organic molecule called pyrimidone. Interestingly, the inspiration for the design came from biology itself. The molecular structure resembles components found naturally in DNA, where similar reversible changes can occur when exposed to ultraviolet radiation. The scientists realized that this same principle of reversible molecular transformation could potentially be harnessed for energy storage. Much like photochromic sunglasses that darken in sunlight and become clear again indoors, the molecule repeatedly changes form in response to light exposure. But instead of simply altering its color, the new material captures and stores solar energy during the transformation process. What makes the system especially impressive is its combination of stability and energy density. According to the researchers, the molecule can retain stored energy for extraordinarily long periods without significant loss. Computational modeling performed with collaborators at the University of California, Los Angeles helped explain why the molecule remains stable while holding this high energy state. The researchers also deliberately engineered the structure to be lightweight and compact, eliminating unnecessary chemical components in order to maximize storage efficiency. The result is a molecule capable of storing more than 6 megajoules of energy per kilogram. For comparison, conventional lithium-ion batteries typically store around 0.9 megajoules per kilogram. By mass, this molecular system can actually hold more energy than many widely used battery technologies. Perhaps the most striking demonstration came when the team showed that the stored solar energy could generate enough heat to boil water under ordinary ambient conditions. Boiling water may sound simple, but from an energy perspective, it requires a substantial amount of thermal power. Achieving this milestone demonstrates that the system is not merely a laboratory curiosity, producing tiny temperature changes. It is capable of storing and releasing meaningful amounts of usable energy. In practical terms, that could eventually support applications ranging from off-grid heating systems to residential water heating and portable energy storage for remote environments. The concept also offers several potential advantages over conventional solar infrastructure. Because the energy is stored chemically within the material itself, there is no need for separate battery systems. The liquid containing the molecules could potentially circulate through rooftop solar collectors during the day, absorbing sunlight and storing energy as it flows. The charged liquid could then be stored in insulated tanks and later triggered to release heat whenever needed, even after sunset. Since the system is recyclable and reusable, the same material can repeatedly absorb, store, and release energy over many cycles. Beyond immediate applications, the research reflects a broader shift in how scientists think about renewable energy storage. Traditional approaches focus heavily on electrical systems and electrochemical batteries, but nature itself often stores energy chemically. Plants, for example, store solar energy through photosynthesis inside molecular bonds. This new technology explores a similar philosophy, using engineered synthetic molecules. Instead of relying entirely on massive electrical infrastructure, future energy systems might one day store sunlight directly in stable chemical forms that can be transported, reused, and activated on demand. There are still major engineering challenges ahead before the technology becomes commercially viable. Researchers will need to improve scalability, long-term cycling durability, manufacturing efficiency, and overall system integration. But the proof of concept is extremely important. It demonstrates that solar energy can be captured and stored in a compact molecular system with energy densities competitive with existing battery technologies. Perhaps most importantly, the work highlights how advances in chemistry and materials science are expanding the very definition of what a battery can be. In this case, the battery is not a metal box filled with electrodes and liquid electrolytes. It is a carefully engineered molecule that traps sunlight itself inside its atomic structure. If technologies like this continue to advance, the future of renewable energy may not simply involve storing electricity, it may involve bottling sunlight directly into